I would like to thank the organizers for the nice possibility to present here my work. This is a joint work with Professor Kotlyarov. We consider the modified quarter-vector Friis equation with the following type of initial data, and we are interested in large time asymptotic behavior of its solution, and especially we will focus on the following small region. We call the line x is equal to 4c squared t the leading edge, and hence we see that this region is situated close to the leading edge. And this region is actually small because we see that on the left border we have small parameter epsilon, and hence it is close to the leading edge, and hence the right border is even closer to the leading edge. But due to another choice of parameterization, we can distinguish a non-small parameter n. N is a natural number. So we see that in some sense the right border is better separated from the leading edge than the left border, which is further from the leading edge than the right border. And I said that we are interested in this region, but actually, yes, we are interested, but we cannot, we don't know how to study asymptotics in this region. What we know asymptotics in adjacent regions from above and from below, and because of this we can make some conclusions about the behavior in this small transition region. Namely, we will say what cannot happen there. We make some technical assumptions about, yes, first of all, we suppose that the solution of this initial value problem exists, and we are interested only in asymptotics. We suppose that the solution at all time exists and satisfy the following integral inequalities, so that it tends to background constants with the first moment. Due to this, we can employ the machinery of Yost solutions, transmission coefficients, and reflection coefficients. All the stuff which is well developed for scattering problem. Also, we suppose that at initial data, tends to these background constants exponentially fast. This is technical requirement which we impose in order to have analytic continuation of the reflection coefficient from the real line and from the corresponding corresponding continuous spectrum. Asymptotics in the domain above the region in which we are interested in was studied by Khruslov and Kotlyarov. They used the method which was introduced by Khruslov for the quarter-vector Friis equation, and this, in its turn, this work by Khruslov, it was I just try to find the right word. Okay, so this work by Khruslov was motivated by previous work of Gurevich and Bitaevsky for the same problem, for quarter-vector Friis equation. Okay, so in the domain above logarithmic curves, the asymptotics has the following form. We see that this expression looks like solitons, and the distinction from solitons is due to this logarithmic phase. Because of this logarithmic phase, this expression doesn't satisfy the modified quarter-vector Friis equation precisely, but they satisfied with some error. There is some error, and this error tends to zero when time tends to infinity. Hence, that's why they called these objects asymptotic solitons. And we see that here we have some constant phase alpha and tilde, which will play important role in this discussion. The influence of the initial profile, uh, it it is presented here in this coefficient alpha and tilde. It comes through this quantity h star, which is in its turn is associated with the transmission coefficient. And so we see that this influence of initial data is relatively small here, comparing with the influence of initial background with this background constant c and 0. The influence of this constant is big here. Yes, it has the following. The asymptotics in this region has the following form. If we suppose the absence of the usual solitons, in general they can be present. They can be presented here, and in this case they will run in front of the leading edge. Their velocity must be bigger than 4c squared. In this, in this, in other, in its turn, we see that close to this leading edge, 4c squared t, in a small logarithmic domain, we have a train of asymptotic solitons, which run almost with the speed 4c squared, a little bit less. And also we see that the centers of solitons lie on the following logarithmic lines. So we see that solitons are supported in the vicinities of these lines, of these logarithmic lines. So again we see that this logarithmic curve, which bound our region, isn't that good choice of parametrization. And each n describes a new soliton. The asymptotics in the region beyond the left border uh, of this region in which we are interested in, it was studied via the Riemann-Hilbert problem method, and the leading term has the following form of a modulated elliptic function. Here, d, the quantity d, which determines amplitude of this wave, is determined through the following system of equations. And parameters b, delta, and tau are determined in the following way, using already defined quantities d and mu. And again, we see that the influence of the initial data of the exact form of initial profile is presented here only in this term delta, in this quantity delta, and that's all. So we can say that it's relatively small comparing to the influence of this background constant c and 0. While the influence of the exact form of initial profile is hidden here just in one function of the ratio of x over t. Well, so still it is quite important. So it's different for every uh, it's different for every it's different for different xi. And The natural question which we can ask ourselves is whether this Q and Q elliptic, whether this asymptotics for Q elliptic can be extended to be right asymptotics in the bigger domain up to the leading edge. And it turned out that Q elliptic has the following asymptotics in the logarithmic neighborhood of the leading edge, which is very similar to what we just seen for Q just 2 slides ago. We have exactly the same domain, exactly the same logarithmic domain, and slightly different error term. Here we have t2 minus 1/2 instead of t2 minus 1/2 plus sigma. But this is not very significant, and the main distinction is in the phase alpha n of xt. Let us imagine that these phases alpha n of xt and alpha n tilde, which we saw before, are also coincide. This would indicate that the elliptic asymptotic is valid in this logarithmic domain. Is also valid in this logarithmic domain up to the error term of t2 minus 1/2 or t2 minus 1/2 plus sigma. And hence, most probably it would also mean that this asymptotic is also valid in the remaining part of this small region from minus epsilon t to minus n logarithm t. But it turned out the situation is more interesting. Those phases they do not coincide. This phase alpha n of xt they're not the constants. They're not constants, but they depend on xt in the following way. They are almost constant in every logarithmic curve of the following type. In the leading order, these phases they are determined only by this constant gamma. Hence, we can ask ourselves a question. Maybe we can change this phase alpha n of xt with some constant, and in that each soliton they are centralized along the following line. Here alpha n of xt is slowly varying quantity, so we can put it in this way. So here alpha n of xt is bounded function. In that we see that every soliton is supported in the vicinity of this logarithmic curve. So maybe we can, and apart from this curve, it vanishes. So maybe we can change this alpha of n of xt with some constant. Okay, so if it's true, then this constant would be the constant which is equal to alpha n of gamma, where we take gamma is equal to 2n minus 1/2. Unfortunately, it turned out that the rate of decaying of these solitons away from their central lines are not fast enough to replace phase just with a constant. So if you take the following logarithmic curve, which lies close to the central curve of this soliton, with some epsilon logarithm t, with the distinction epsilon logarithm t, then the soliton will be of the order t2 minus epsilon multiplied by some constant. Okay, so if we change the phase with a constant, then the results in asymptotic soliton with the results in elliptic soliton with on this line with a constant also will be of the order θ minus epsilon, but with some other constant. Here we have alpha n of gamma evaluated at the point 2n minus 1/2 minus epsilon, and here it's evaluated at the point 2n minus 1/2. So these are different constants, and hence the difference between these two expressions will be also of the order θ minus epsilon, which is bigger than admissible constant, that admissible error of the order θ minus 1/2. So we see that this is essential, that the phase in this elliptic solitons is a function of xt and not just a constant. And this already shows that q elliptic and q do not coincide. Let us also take a look at alpha sub n at the peaks of elliptic solitons. Nevertheless, let's take a look at this alpha sub n at the peaks of elliptic solitons. What do we see? We see that these expressions for alpha sub n and for tilde alpha sub n are actually very different. So alpha n of gamma has the following form, and alpha n tilde has the following form, so they are very different. But in the limit when n tends to infinity, these quantities became closer and closer to each other. If n and t tends to infinity, simultaneously and this suggests a hypothesis that q elliptic and q are close to each other for both n and t large. When they are large, согласовано. I need to take a look how translate this word in English. But the mechanism how this occurs is unknown for us. And in conclusion, I would like to say, so this is a statement of the problem, which actually we don't know how to solve. I will just tell how, just showed a brief description of the methods for finding asymptotic solitons and the method for finding this modulated elliptic wave, and for decomposition of this modulated elliptic wave into this solitons with logarithmic phase. So the method for asymptotic solitons, it was developed by Khruslov for KdV, and then it was extended by Khruslov and Kotlyarov for MKdV. So it is based, yes, first of all, they considered much more general situation. Their backgrounds were not just constant, they were even some finite gap functions. But in our particular case, so our particular case is just our case of a constant background is just a particular case. So they based on Gelfand-Levitan-Marchenko equations, which for modified quarter vector phase equation takes the following form. It is a system of two equations, and this is because like Spera for modified quarter vector phase equation is a matrix. 2 times 2 matrix is a matrix, as opposed to the KdV equation where it is scalar function, scalar quantities. The kernel H is defined here as an integral over continuous spectrum, which is now a real line and an interval on the imaginary axis from IC to minus IC. And we see that if we are slightly below the leading edge, then they notice that in the neighborhood slightly beyond the leading edge, x is equal to 4c squared t, the main contribution to h, to this kernel h, is given by integration of a small small interval from IC to IC minus epsilon, since the other part of integrals are exponentially small. And new variables psi, eta, and zeta, which are obtained from x, y, z by subtracting 4c squared t, the main part of the kernel can be written in the following way. Now, in the region where we are interested in, that is, which is slightly below the leading edge, the exponential of zeta plus eta is decaying, and this term zeta plus eta is decaying, and hence they could expand it in the series. Then they proved that the residual series gives smaller contribution than partial sum of the series, and they replace exponential in the integrand by its partial sum. So they come to degenerate Volterra integral equation, solution of which they could find in the following form. And this gave them expressions for asymptotic solitons. Now let us take a look at the Riemann-Hilbert problem from which we get Q elliptic. So the problem is the following. We are looking for 2 times 2 analytic function which has jump across the following contour, which is depicted in this picture, with the following and has the following jump condition along this contour. So it has some jumps. Here G is here quantities B and delta we already defined, and also D we already defined before, and G, F, are the following function. So G is determined in terms of quantities mu and D, and F can be found as a solution of the following conjugative scalar product along the interval IC to minus IC. And the solution of the modified Korteweg-de Vries equation is connected with the solution of this in the following form, and for the Q elliptic we have the following formula. And now here are some technical details how we expand this elliptic formula into these asymptotic solitons. So this is quite technical task. I will just mention just few ключевые моменты. So the first ключевой момент is that theta series, which represent these theta functions, are in the limit when we are close to the leading edge, they became slowly convergent, because this b period tau of the corresponding Riemann surface tends to 0. So we can overcome this using Poisson formula. Then the series became fast convergent. This is first thing which I wanted to mention. Then it's technical. We just rewrite it in the following form, and here we see that each term, each theta functions actually in each series which represent theta functions, the main input is given just by 2 or 3 main terms, and hence we can write asymptotics of this expression in the following form. So here we already have some objects which are already cosinus hyperbolic, and now we need to express this argument of this cosine in terms of x and t, and we can do this, and we find the following form, and we find the following asymptotics of this argument. And the last thing which I would like to mention is to express this in terms of x and t. We need to find the asymptotics of some integrals. For example, we need to find asymptotics of I1, I0. So the asymptotics of the integral I1 as d tends to 0, as d tends to c can be found quite easily. We just make change of variables. Well, yes, this is easy integral. No, sorry, I mean if you want to find the asymptotics of I0, this is easy. This is easy. We just make change of we just change the interval of integration from d to c to the interval from 0 to 1, and then we just expand the integrand, and doing this we find the asymptotics of the whole integral. But it's another situation with the integral I1. Here we cannot do this. So because if we take the limit d tends to c, then the integral will become disconvergent. And the way how to find asymptotics of I1 lies in this formula. In this formula we know already asymptotics of I0, and next we have the following connection. We have the following formula which connects the parameter tau and the parameter d, and hence the parameter t star. And from this formula we can, since these series which represent theta functions are fast convergent, then we can express we can find asymptotic expansion of this tau star in terms of d. Here eta is some linear combination of d, which tends to 0. And then we make a lot of technical work and find the decomposition of this elliptic wave to this asymptotic solitons. That's all. Thank you very much for your attention.